morning.
Good morning.
So you are, as Kagglers may or may not know, not actually on the Kaggle team. This is Jacob Devlin, who is a research scientist at Google.
Hi.
Hi. And we've talked on the channel quite a bit about the BERT paper. We actually read it in a live stream, and you are first author on that paper.
Yes.
Yeah. So do you want to talk a little bit about, besides like one of the BERT authors, what it is you do? What's your day-to-day like?
So I'm a researcher on the NLP team, and so as researchers, we generally have a lot of autonomy to kind of work on the type of projects that we think are interesting. So I like question answering. So question answering has become one of the dominant types of research in NLP in the last 2 years or so. Partially it was motivated because of academically, at least the release of the squad data set kind of put all that in motion. But in general, like a lot of things can be framed as question answering. Like almost anything actually can be framed as question answering. And so if you kind of take a very broad approach to it, you know, it's solving kind of almost all aspects of natural language understanding. And so now that kind of the standard NLP tests like parsing and stuff like that have become somewhat outdated because everyone's going to end-to-end systems, kind of that's something that a lot of people have converged on. In addition to like machine translation is another big one that people are working on. So a lot of my focus has been on the production question answering system at Google and kind of trying to bring that up to date with the state of the art, and that's where kind of BERT came out of, was kind of a technique that I had worked on there. And then the way that it actually happened was that I was using this idea for using a masked LM to do pre-training was something that I had, and I was successfully using it to improve Google's internal question answering system.
That was bi or just the unidirectional?
That was the bidirectional one. So that was the main novelty, right? Because it was because it didn't really make sense to train a unidirectional one because the models that we were using were bidirectional. And then I was aware of Elmo because Kenton Lee, who's another author, was one of the authors of Elmo, and it also was very popular. But I wasn't as big of a fan of the kind of the contextual embedding thing where you just kind of feed it in. I like kind of the more training a model and then fine tuning it approach, because that way you don't have to waste, or you basically everything, all your parameters are pre-trained. Then the OpenAI paper came out, and the results were just like kind of absurd how good they were for like just training a big language model. So I started to run some ablations on that because my model was not as good initially, and then I quickly realized that the big thing was just that they trained a huge model, like a 12-layer model, which was quite large at the time. Like the transformer big model was only 6 layers, and so then when I did the master limit with 12 layers, and then it just started to work really well, and then it seems like kind of the sky's the limit in terms of at least model size and how well that works. So yeah, that's kind of how that happened.
Cool. So you were working on something to improve something that was already in production, and then you sort of came up with a new approach, or excuse me, this chair is very creaky, modification of existing approaches. And to me, the thing that I think is most interesting about BERT is the masked aspect of the training task. And I guess, of course, the sentence prediction is also looking at the ablation studies very helpful. But how did you come up with the masking task?
I mean, that's a fairly standard task in NLP called the closed task that's been around since like the 50s. It was originally I guess it was a task that was used by educators to kind of assess reading, like what reading level a child is at by how well they can complete sentences. And so when I told my mom about it, she's a teacher and she was very familiar with this as a task in education. And so yeah, it's kind of, I think that the idea of using it to train a model is a little bit obvious. I think that really it's just you're kind of making a trade-off with computational cost, because normally with a language model you have this nice trick that the number of predictions you make is the same as the number of input words, And so with this model, you can only predict a small amount of words, and that's where all the signal is coming from, right? So it's unclear exactly, at least before this result, it was unclear how much longer you would have to train the model to get the same accuracy, because you're getting so much less signal from the back propagation, but you still have the same number of words in the input. So it's clearly somewhere between like if you mask one out of every 7 words, it's going to be somewhere between the same amount of time and 7 times as long. We didn't know exactly how long it's going to be. And it turns out it's more like maybe like 20 or 30% longer, which is not very much. And so it was, so it was worthwhile from that point. And I think that largely it was that people had not really tried this at scale before. I couldn't actually find any citations where people actually directly used a masked LM, despite the fact that kind of people have used this for like evaluating models before. People have not really tried to pre-train at scale with it.
Yeah, that makes sense, especially like certainly when I was doing my NLP coursework, we started with n-grams, and like it was like you're going to go through and look at each word in the sentence, or your text or whatever span you're looking at.
Yeah, I think the kind of left to right language models were very largely ingrained in people's minds as kind of the way to do language models, and so this wasn't as, because it also it's not like a probability distribution anymore over the sentence, and so that, but we don't care about that. Like, you only care about that if you're actually trying to model use it for speech recognition or machine translation or something where you actually need to generate a probability distribution.
Yeah, but for things like question answering where it's more constrained.
Yeah, well, no, I mean, so it's not that it's because we're not actually using like a language model. We don't actually, like, you still need to generate probability distribution at the end of the day, but not for the actual probability of the sentence, because the sentence is given to you at test time.
Yeah, and you're not generating or picking words given, your various inputs. Yeah. So are you still working on sort of like more applications or productionizing this, or are there other things that you can talk about that you're working on now?
Yeah, so one big one, certainly inside of Google and probably outside also from what people have been saying, is kind of the speed of the model. So it's quite expensive, which is.
And this is a training time, right?
Yeah, well, it's expensive to train, but that's actually not that big of a deal because you only have to do that once, really, and then you can kind of reuse the same component. It's more for trying to serve it is quite expensive. And so I am working on a lot of kind of general techniques for how to kind of distill it into a smaller model. So there's this kind of well-known technique called distillation, but it's really just kind of also semi-supervised learning, where if you have a bunch of unlabeled data, and then you pre-train your model on unsupervised data, which could also be your unlabeled data if it's domain-specific data, like whatever medical text or web crawl data.
Sure.
And so then you maybe only have like a few 100,000 labeled examples, and so you pre-train on this huge corpus. You fine-tune on your few 100,000 labeled examples. But then if you also have millions or billions of unlabeled examples that look like your training data but aren't labeled, which is the case for a lot of companies because you have log data from users and other things like that, then you can just label that with your system and then retrain a much smaller model. And because now and get a lot of the gain, because the smaller model is not as powerful, but when you give it millions and millions of training examples, it can kind of close the gap, because it's not really just memorizing the data, but it's kind of learning
patterns.
Yeah, it's kind of like, so I mean, I guess the hypothesis kind of gets into why does pre-training work so well. And so, because the simple explanation is that it's learning contextual embeddings, right? Like bank is bank account, but it's clearly more than that, because it's almost clearly like it's learning models that are it's learning like millions of like latent, like in order to do language modeling well, whether it's left to right or masked LM, you have to learn pretty much all aspects of language understanding. And so you're kind of learning latent features for everything, for co-reference, for semantics, for syntax, for like understanding temporal relations, like basically everything you need to do in language understanding has, in order to do language modeling well. And so when you train, so the reason why these models have to be so big when you're pre-training them and have to train on so much data is that for any given task, maybe you learn millions of latent features, but maybe only a subset of these features are actually useful for a given task. And so you're kind of over-learning. And so when people had, I'm sure people had tried this 5 years ago or more, but because they probably tried like the same size models that they were using for their state-of-the-art, sentiment analysis system or whatever, then they weren't getting very good results, because it turns out that you actually need to scale up the models to be much bigger so it can kind of learn all this extra stuff and then hope that learn the thing that you actually need.
So especially if you're looking at like a rare construction, if it only occurs once every 100,000 sentences, you need to train on millions and billions of sentences in order to have a good sample to learn the feature of that, whatever it is.
So it's both the size of the model, like the number of layers, and also the amount of data you're training on. And so you really need both of them to be quite large to get good results, which we show in the paper. So that was, I think, what, like, compared to like the previous work, I think that was actually one of the most interesting parts of the paper, was the showing the ablation, to show that you really do need, because the other paper just kind of had these big models and then showed, well, this works well, but showing that you actually need to train it over such a large amount of data and such big models was kind of very interesting to me. Like, I wasn't expecting that to be such drastic improvements for these small scale training tasks. And so, but that also would imply that's why distillation works so well, because once you kind of now have trained a model for one specific task, now you can kind of compress. You don't need such a big model at serving time. You can, if you can label a bunch of data, you can kind of compress it down to only do this task well. So this model won't do other things well, but it will do this one thing very well, which is what you typically want. And so I think all these things are kind of related in terms of like why you're able to distill the model so well, and also why the model had to be so big in the first place.
Yeah, it's definitely something that, I mean, even just while I've been working, compute availability and just the ability to work with very large models and train them for a very long time has become feasible.
Yeah, I think I think that before, a few years ago, like, this just wouldn't have been even not just BERT, but the other models just wouldn't have been feasible. It would have been like 6 months to train a model, and you wouldn't ever have even been able to do the experimental cycle because of how long that would have to take in, and yeah,
it would be like building a house, and then it's really hard to build a second house that has a chimney in place and see if people like it better.
Yeah, I mean, the downside though is basically, no matter how much, the absolute results keep getting better, but like no matter how much faster hardware gets, it keeps taking like 4 days to train an experiment, whether it's because like there's kind of a limit of how long researchers are willing to wait for the experiments to run, and then you just scale it up until you hit that point, and then your absolute results get better, which means that the papers get better, and so everyone else needs to do that same thing to match it. So there definitely is, a lot of kind of I think that like there's a certain amount of, in the academic community, there's a certain amount of kind of concern about, given that these enormous pre-trained models do so well on basically everything, what can we kind of work? Because historically, like, everyone knew that like training gigantic models works really well in language modeling, where you have an infinite amount of data, and works well in machine translation, where you have a very large amount of data. But the argument was like, well, okay, there's these 3 tasks where it does really well, but I have these other 10,000 tasks for which I only have not that much data, and so I can't just build a gigantic model. But now if it turns out that you can, then not everyone has access to those resources, and so it is a little bit scary, I think, for a lot of people, because if they don't have access to figure out how to exactly to compete. And I don't actually have like a good answer to that, but I think it's something that's kind of have to, the community is going to have to kind of sort out exactly what that's going to mean.
Yeah, it's tricky, and it's something that we run into at Kaggle competitions as well, because if you have like $3,000 to spend on compute, you can build just like a better model because you have the access to those resources. So we've been launching some kernels only competitions, which is your submission has to be made through our hosted VMs, and everybody has the same one, and that helps. But I mean, you're not necessarily going to get state-of-the-art models in, you know, little VM.
So in that case, the training has to also happen there, or is it?
Yeah. So your submission goes through that, and we at the point where the final scores are assigned. Wow, I finished my coffee. We have data set that matches the format of the other data set, but has a new distribution that's unknown, and then we run it through their kernels, and the output is the final thing that's scored.
Oh, okay, that's interesting. Yeah.
Yeah, which is like interesting for shared tasks, but does make it a little bit harder if you want to say put things into production.
Yeah. Yeah, I mean, I think that like yeah, I mean, I don't really know the answer. I was talking, some people were saying, you know, maybe we should try to find tasks where pre-training doesn't work as well, because that, you know, then it's like, but I don't think any such, like, it's hard, like pre-training is just learning a system that understands language. So if you have a language understanding task, it's hard to imagine a case where pre-training won't work as well. I mean, I think it's certainly, it's not like, it's certainly exciting for people who are building systems, right? Because the absolute results are getting way better. And it's kind of enabling stuff. So I think like inside of Google, people are really excited because, you know, they can improve their product and get huge things. And in other companies, I'm sure the same thing too. I think people are also excited because they can kind of publish, like, there's like a first round of papers where they can say, okay, we took BERT or Elmo or whatever. Like when Elmo came out, there was the same thing where there was a huge rush paper saying, like, hey, we got state of the art by applying Elmo plus thing. And it's like, you know, if people get state of the art by a few points, it's basically got to get published. So there's kind of a gold rush. But then once that kind of like first gold rush kind of ends, I think it's unclear exactly what the next steps should be for the community. Because there's obviously a lot of work on pre-training itself. Like this BERT is certainly not going to be the last, like the end all be all of pre-training. But again, because that's so computationally expensive, then it's kind of limited to the people from the big labs. And so I think that is a little bit unfortunate. But I mean, yeah, I don't know if there's a great solution to it.
Yeah, it's hard. No problem. Speaking of things that are hard / interesting, is there any other work besides pre-training? Because I think we've touched on that quite a bit, that you're just very excited about right now, or papers or blog posts you read recently that have been really cool.
I think the recent work on GANs for image recognition have been really cool. And I'm wondering, yeah, like it feels like it's kind of the right solution for a lot of, because a lot of the problem with text like NLP problems is that like evaluation is impossible because you don't have more than one reference, or you only have one reference, and there's lots of possible answers. Like, you know, there's an exponential number of possible answers, and so that kind of creates a problem at training and evaluation time. So it does kind of feel like GANs are potentially the kind of answer for a lot of issues, like how can we make like chatbots more interesting? Because if you just train for maximum likelihood, you get pretty boring chatbots.
Yeah.
And so like maybe GANs are the right kind of answer for chatbots, but I don't really think anyone's kind of had the right recipe for text yet.
Yeah.
And so I tried a little bit for machine translation. I didn't get good results. I think it's like a very subtle, because like if you're kind of, if you have a sufficiently smart GAN, like if your reference is even one word different than what your system would produce, then it can trivially tell. And so I think it's hard to kind of really match like human distribution for text, because of like you have to do like very careful filtering and really make sure that your data. But I think maybe for like cleaner data sets, because machine translation data tends to be pretty noisy, I would imagine that it would help if you kind of did it right. Like for image captioning, maybe like something like that. That might be. I would imagine that would be a decent, where it's kind of it's still constrained, unlike like more so than chatbots, but it's kind of like you have like a nice clean data set, and that's also a thing where you get like, you know, if you just train it for the standard way, you get kind of very boring captions, and so that might be something where people can. But yeah, I haven't seen papers on it, but I think that kind of the just the quality of the the GANs for image recognition have kind of indicated that like this is such a like powerful method in general.
Yeah, definitely. I wonder if there's that NACL workshop on evaluation methods for text generation. I'm wondering if anyone's going to have a GAN paper in there.
Yeah, I think that definitely, I would imagine they would. I think it's going to be hard to do it. I think the evaluation, like, because evaluation is even a big deal for images, right? Like they use these weird evaluation metrics I don't really understand, but it's mostly just showing examples and then people assuming you didn't cherry pick it too badly. And like, yeah, because I think that like the space of possible, like again, that can kind of truly discriminate across all possible pieces and can't be gamed. Because once you release an evaluation metric, then people should be able to tune towards that evaluation metric discriminatively, and so therefore, if your metric can be gamed in any way, then you're going to be like, it's not that the researcher is being dishonest, it's that the machine learning system that is trying to, like, by definition game the metric. And so yeah, I think that'll be a more, because the problem with evaluation of text has always been that issue that you tune something towards blue and you evaluate it on a different metric, and then it does well, but then once you actually tune it towards that metric, then suddenly you realize it just produces like it produces sentences that are like, you know, infinitely long, because it's like, hey, this metric only measures precision, or only measures recall, doesn't measure precision at all. Yeah. And so stuff like that happens all the time. And so yeah, I think, but I mean, GANs are theoretically kind of direct, because the whole point is that you have this minimax problem, so that it's kind of covers all possible inputs, but you know, in practice, you know, it's unclear whether that's really true or it just kind of converged to whatever the last one was. But yeah.
Yeah, it'll be interesting to see more work in that. And I don't think I've ever seen anything personally with GAN and text that I've been excited by, but we'll see.
Yeah.
And is there anything else you want to share with the Kaggle community? I know there's a data set that was released relatively recently. I want to say this month.
Oh, the natural questions?
Mm-hmm.
Yeah. So our team, the team in New York released a question answering data set that so like Squad and a lot of the other question answering data sets, the big problem is that they're generated by crowdsourced workers, and typically they see a paragraph and are asked to write a question about that paragraph. And so in this case, these are real questions, and they were taken from Google Suggest, so that's the ones that everyone can see already, so there's no like privacy issue there. And then we had annotators take those real questions and then annotate in a Wikipedia article like both the paragraph and like the short answer that answers that question. And we released a large data set of this. And so the gap applying state-of-the-art BERT models is, you know, way higher. The gap compared to human quality is like 20%, whereas for Squad it's now like either, depending on the data set, like less than 1%, or just because of this kind of issue of the overlap being unrealistic. So this is not only is it, you know, it's harder, but it's harder in a meaningful way rather than just making it harder synthetically, because it's all real data. And so we're hoping that people will kind of start to play around with that and start to kind of maybe figure out what type of new techniques are actually needed to close the gap with humans.
Yeah, definitely. It'll be good to see work coming out of there. Is there anything else you want to share or bring up?
I think so. One piece of advice I always give to PhD students and people is it's not considered rude to like reach out to a researcher specifically that you want to work with and like email them. It's not considered presumptive or anything like that. Like that's actually how most internships are made, is by somebody kind of taking the initiative and reaching out and saying, hey, I really like this work, and I thought that like this extension would be interesting. People in general really like that. It's like it's kind of, because generally when you have an intern, you kind of want one that's fairly self-motivated and confident, because you don't want, like, you are doing your own work, and so you like somebody who kind of seems that they're kind of in control of things, and kind of knows what they want to work on. Mm-hmm. And it's also hard to, there's so many like kind of internship, if you just go to like the standard page of interns, like there's so many of them and so kind of creating that personal connection is something that yeah, it's something that is it's not like considered like road or inappropriate at all. And so I would definitely suggest, you know, like kind of doing that with when you want to get an internship. So even like as an undergrad, potentially, if you have some amount of research experience, that you can get an internship. And you know, and also like don't just like email like the really famous researchers, like don't just email like Ian Goodfellow or whatever. Just email like, you know, like try to find people who have like papers that you think are interesting at companies that you kind of want to work at, that maybe aren't as well known, and then you have a better chance of kind of getting an internship with them there.
Yeah, that's really good advice. Thank you. All right. Thanks for joining me. I'm gonna start wrapping up here because I don't want to go too long. Yeah. It's been Jacob Devlin, Google researcher, and thank you.
All right, nice talking to you.